This is Lesson 27 in our Calculus 2 series, Conic sections. Consider the curve of intersection of a cone and a plane. These curves can fall into three main categories: the parabola, the ellipse, and the hyperbola. And these are called conic sections. Note the degenerate cases when the plane goes through the vertex of the cone. Here the intersection is just one point, and here we have an intersection that is a pair of lines. But we're not interested in these cases, and we're going to focus on the conic sections for this lesson. A parabola is a set of points in the plane equidistant from a given focus point and a given directrix line. So here's our focus point. Here's our directrix line. And so the parabola is the set of points equidistant from both the focus and the directrix. So that says for any point on the parabola, the distance to the focus is the same as the distance to the directrix. Parabolas have the property that waves traveling into the parabola parallel to the principal axis reflect off the parabola wall to the focus point. This is useful in reflecting telescopes, satellite dishes, radar receivers, and solar furnaces. Similarly, if the focus point is the source of your waves, then the waves will reflect off the parabola wall and out parallel to the principal axis. This is useful in the design of car headlights, where it's important to have the light focused in the proper direction. Also, we know that with projectile motion, objects follow parabolic trajectories. So throwing a ball or hitting a baseball, punching a football, shooting a basketball, the trajectory of the ball would be that of a parabola. Same thing with a water fountain and when you're playing Angry Birds. And so in general, with projectile motion, if we start with an initial velocity and the angle of incline, we can predict how far the object will travel and how long it will take to get there. And this is all talking about projectile motion near the Earth's surface and neglecting air resistance. So near the Earth's surface means gravity is governing the downward acceleration, and neglecting air resistance means this is useful for objects that are going somewhat slowly. For something like a bullet, air resistance plays a bigger part, and this wouldn't be as applicable. Also, you might have heard of NASA's KC-135 Vomit Comet, the aircraft that can simulate zero gravity. It takes parabolic paths to create that zero gravity effect. In any case, let's continue on with our parabola. When a parabola is centered at the origin, if it is an upward or downward facing parabola, the focus will be identified as 0p, and the directrix line will be y equals negative p. And so here we're showing for p greater than 0, and here for p less than 0. And going back to the definition of the parabola, where we said for any point on the parabola the distance to the focus and to the directrix are the same, if we set those two distances equal to each other, we'll get the equation x squared equals 4py for parabolas that open upward or downward, centered at the origin. So for example, find an equation of the parabola with focus 0, 3 and directrix y equals negative 3. If we know the focus is 0, 3 and the directrix is y equals negative 3, we have this situation here. So we know that p is equal to 3. And so the equation we're looking for is x squared equals 4 times 3 times y. So we can say x squared is equal to 12y, or if you want to solve for y, y equals 1/12 x squared. Similarly, for parabolas that are opening to the left or to the right, our focus is identified as p, 0, and the directrix x equals negative p. Focus p0, directrix x equals negative p. So here we're talking about p positive, and here we're talking about p negative. And the equations here are of the form y squared equals 4px. So find an equation of the parabola with focus negative 4, 0 and vertex 0, 0. Okay, we have a focus of -4, 0 and a vertex of the origin. So we're here in this picture. And so we know that P is equal to -4. And so y squared is equal to 4 times -4 times x. So y squared is equal to -16x, or if you want to solve for x equals -1/16 y squared. Another example, find the focus and directrix of the parabola y equals -2x squared. Well, notice that we have x squared here, so this must be x squared equals 4py. This equation must fit the form x squared equals 4py. So in order to set these equal, let's solve for y here. We get y is equal to 1/4px squared, and we set that equal to -2x squared. And so -2 is equal to 1/4p, and so p must equal -1/8. And so our focus is going to be 0p, which is 0, -1/8. And our directrix is going to be y equals -p, or y equals 1/8. Now let's take a look at shifted parabolas. We had the vertex at the origin for the parabolas we were just looking at. Now let's talk about a parabola with vertex h, k. In this case, we just need to replace x with x minus h and y with y minus k in all of our formulas. So for the upward and downward facing parabolas, we had before y equals -p for the directrix. Now replacing y by y minus k and bringing the k over to the other side, we get y equals k minus p. And shifting the vertex to hk, we notice shifts the focus to h, k plus p in these cases. And so the equations here are x minus h squared is equal to 4p y minus k. Similarly, for the sideways facing parabolas, we have y minus k squared is equal to 4p x minus h. We have directrix x equals h minus p, and focus h plus p, k. I think the easiest way to remember these formulas is really just to remember the initial image at the origin and then think about the shifting. And it will become easier to remember where to add the p, where to subtract the p, that kind of thing. So for example, find an equation of the parabola with focus 3, 6 and vertex 3, 2. So the first thing I want to do is get an idea of what this parabola looks like. So I'm going to plot the focus 3, 6, that's here. I'm going to plot the vertex 3, 2, that's here. Now I know the parabola is going to open towards the focus. So I know that it's going to be an upward facing parabola here. I know the distance between the vertex and the focus is 4 units. That tells us p is equal to 4. So if we're looking for the equation, we know we're going to have x minus h squared is equal to 4p y minus k. P is equal to 4, so our equation looks like this. X minus 3 squared is equal to 16 times y minus 2. Remember, hk is our vertex, so that's 3, 2 here. And so we have x minus 3 squared is equal to 16 y minus 2. Now let's take a look at the ellipse. An ellipse is a set of points for which the sum of the distances to two focus points is constant. So we're starting with these two focal points, and we're looking at the set of points for which the sum of the distances is constant. So that says for any point on the ellipse, the sum of these two red lines must be the same as these two blue lines, for example, because this blue point is also on the ellipse. So the sum of those distances is constant. We have a couple of interesting applications of the ellipse, or the 3D version, the ellipsoid. A lithotripter is a device used to break down kidney stones by sending sound waves from one focus point through an elliptical-shaped chamber directed towards the kidney stone, which is placed at the other focus point. And so this is a non-invasive way to break down the kidney stone. Also, you might have heard of whispering galleries, where whispers occurring at one focal point can be heard on the far side of the room at the other focal point of the ellipsoid, because the sound waves from one focus reflect off the ellipsoid wall and to the other focus. Also, we know that the planets orbit the Sun over an elliptical path, where the Sun's center of mass is at one focus. So let's take a look at the equations. Let's start by looking at ellipses centered at the origin. If the focus points are on the x-axis, we call the x-axis the major axis. And then the y-axis is the minor axis. So the focus points of the ellipse are going to be positive and negative c, 0. The vertices are going to be positive and negative a, 0. And then notice the distance b to the top of the ellipse. We have points 0b and 0, b along the minor axis. And the relationship we have between a, b, and c can be shown by this right triangle. B squared plus c squared is equal to a squared. And then in this case, the equation of the ellipse is x squared over a squared plus y squared over b squared is equal to 1. If we have our focus points along the y-axis, they will be identified as 0c and 0, c. And similarly, our vertices are going to be 0a and 0, a. And the points on the minor axis, negative b0 and b0. And the equation here is x squared over b squared plus y squared over a squared is equal to 1. So for example, find an equation for the ellipse with foci positive and negative 2, 0 and vertices positive and negative 5, 0. I think it's always helpful to get an idea of what the ellipse looks like as graphed. So we have foci positive and negative 2, 0. We have vertices positive and negative 5, 0. That tells us that our ellipse has the x-axis as its major axis. So at this point, we don't yet know how tall the ellipse is going to be. We don't know what that value for b is, and we're going to need that for the equation. So we know the equation is going to look like x squared over a squared plus y squared over b squared is equal to 1. We know that c is equal to 2, a is equal to 5, and we know that b squared plus c squared is equal to a squared. So let's find b, and then we can plug it into this equation. B squared plus 2 squared is equal to 5 squared. So b squared is equal to 21, and b is equal to radical 21. And just to get an idea of what kind of number radical 21 is, to approximate it for our graph, we recognize that radical 21 is between radical 16 and radical 25. So radical 21 is between 4 and 5. So we can go back up here and have a sketch of our ellipse. And to answer the question, we wanted to put b into our equation, so we have x squared over 25 plus y squared over 21 is equal to 1, and that's the equation we're looking for. Another example, find the vertices and foci of the ellipse and sketch the graph. 9x squared plus 4y squared is equal to 36. Well, the first thing we notice is that it's not in standard form, so we definitely want to divide everything by 36 to get it in standard form. Then, from there, you should be able to find the vertices and foci. So please pause the video and work on that. So dividing by 36 gives us x squared over 4 plus y squared over 9 is equal to 1. Since the 9 is bigger than the 4, we know that the y-axis is going to be the major axis. So this is going to be an ellipse that is taller than it is wide. And so a is equal to radical 9, that's 3, and b is equal to radical 4, that's 2, and we know that b squared plus c squared equals a squared, so c squared must be equal to 5, and c is equal to radical 5. So c is equal to radical 5, and we have an ellipse that is taller than it is wide. That tells us our foci are along the y-axis, so our foci are 0, positive, negative radical 5. And the vertices also along the y-axis, 0, positive, and negative 3. because this is positive and negative a, and a is equal to 3. And so our sketch looks something like this. Similar to what we had for parabolas, we could shift the center of our ellipses. So for an ellipse centered at h, k, again, we're going to replace x with x minus h and y with y minus k. And then we'll notice that the vertices and foci have shifted coordinate values as well. And our equations look like x minus h squared over a squared plus y minus k squared over b squared is equal to 1, or x minus h squared over b squared plus y minus k squared over a squared is equal to 1. And for example, find the vertices and foci of the ellipse and sketch the graph, and we're given x squared plus 2y squared minus 6x plus 4y plus 7 is equal to 0. Well, we know that we need to get this ellipse in one of these forms. So that means we're going to have to complete the squares for the x and y terms. So we start by collecting our x terms and our y terms together. For the x terms, we have x squared minus 6x. We recognize that these are the first two terms in x minus 3 quantity squared. So if we want to recognize this as x minus 3 quantity squared, that includes a plus 9, we need to then include a minus 9 to keep that the same as what we were given. So we have x minus 3 quantity squared minus 9, and now let's take a look at our y terms. To complete the square, when the coefficient is not 1, we need to factor out this coefficient of y squared. So we need to factor the 2 out from all of the y terms. And so now we have a 2 outside the brackets, y squared plus 2y inside the brackets, and we want to complete the square inside the brackets. We have y squared plus 2y and recognize those to be the first two terms of y plus 1 quantity squared. But this also includes a plus 1, so we need to subtract a 1 to compensate. And this all happens inside the brackets, so that when we go to simplify, we have to multiply this 2 by the negative 1 as well. Now we can take all of our constant terms to the right side, and we have x minus 3 squared plus 2y plus 1 squared is equal to 4. And to get the form of the ellipse that we're looking for, we want to divide by 4. So we have x minus 3 squared over 4 plus y plus 1 squared over 2 is equal to 1. And we're asked to find the vertices, the foci, and to sketch the graph. We know that the major axis is parallel to the x-axis because the 4 is bigger than the 2. So we have a is equal to 2, b is equal to radical 2. To find the foci, we're going to have to find c. So we solve for c using b squared plus c squared equals a squared. And we get c squared is equal to 2, so c equals radical 2. So we have our center at 3, negative 1, and our major axis is parallel to the x-axis, which means the x values are changing for the foci and vertices, but the y values are staying the same. So we're going to add and subtract an a of 2 from the x value of 3 to get our vertices. And we're going to do the same with c equals radical 2 for our foci. So we have our vertices at 5, negative 1, and 1, negative 1. And we have our foci at 3 plus or minus radical 2, comma, negative 1. Now let's take a look at a hyperbola. A hyperbola is the set of points for which the difference of the distances to two focus points is a constant. So with the ellipse, we had the sum of distances to the two focus points being constant. Now we have the difference of distances from two focus points being constant. And so for any point on the parabola, we're saying take a look at these two red distances, find the difference. That difference is going to be the same as the difference between these two blue distances for any other point on the hyperbola. A couple of common applications of the hyperbola. One example is with trilateration problems, as with the LORAN navigation system. A ship can determine its location by using the signals it receives from 3 fixed LORAN stations. So, coupling them 2 at a time, the ship can tell how much closer it is to one station than the other. So it knows the difference between these two distances. and that's as much as it knows. Similarly, it'll know the difference between these two distances, taking station 1 and station 2. So that is saying that the ship knows that it is on this branch of this hyperbola and also this branch of this hyperbola. Remember, all points with the same difference to two fixed points fall along the hyperbola. And that difference would be positive or negative depending on which one it's closer to, and so the ship knows which branch of the hyperbola it's on. And by using 3 stations, it can find 2 hyperbola branches on which its coordinates lie, and so its location is at the intersection of those 2 branches of hyperbolas. And while I don't believe the Loran navigation system is in effect any longer, it was used for decades. Also, if we take a look at a 3-dimensional version of the hyperbola, the hyperboloid of one sheet, we recognize that nuclear cooling towers are modeled on this shape. It maximizes the strength of the structure while minimizing the material used. So let's take a look at their equations. Centered at the origin and going through the x-axis, we have the equation x squared over a squared minus y squared over b squared is equal to 1. Again, positive and negative a, 0 are the vertices, and positive and negative c, 0 are the foci. And the relationship here between a, b, and c is that a squared plus b squared is equal to c squared. Notice that with the hyperbola we also have asymptotes, y equals negative b over ax and y equals b over ax. For hyperbolas going through the y-axis, we have similar equations. Y squared over a squared minus x squared over b squared is equal to 1. Same relationship here between a, b, and c. We have a squared plus b squared equals c squared. And our vertices are 0, positive and negative a, and foci 0, positive or negative c. And here we're reversing the roles of x and y, so the equations for the asymptotes are x equals b over a y, and x equals negative b over a y. Find the foci, vertices, and asymptotes of the hyperbola 4x squared minus y squared is equal to 16. So we definitely want to divide by 16 here, and that's going to give us a form that we're more comfortable with. We have x squared over 4 minus y squared over 16 is equal to 1. And this is of the form x squared over a squared minus y squared over b squared is equal to 1. So we know that a is equal to 2, b is equal to 4, and then c squared is equal to a squared plus b squared, so c squared is equal to 20, and so c is radical 20, or 2 radical 5. Since we have a positive x squared term, we know that our hyperbola goes through the x-axis, and so the vertices and foci here are going to be along the x-axis. And so we have for foci positive or negative c, 0, so that's positive or negative 2 radical 5, 0, and vertices positive or negative 2, 0. And the asymptotes in this case are going to be y equals positive or negative b over ax. So that's 4 over 2x, or positive or negative 2x. Let's take a look at shifted hyperbolas. Just as we did with the parabola and the ellipse, we can replace x by x minus h and y by y minus k, and shift our coordinates appropriately here. So with the equations of the asymptotes, we're replacing y by y minus k and x by x minus h. And our equation here looks like x minus h quantity squared over a squared minus y minus k quantity squared over b squared is equal to 1. And for hyperbolas in the other direction, we have a positive y term, so we have y minus k squared over a squared minus x minus h squared over b squared is equal to 1. And so let's take a look at one last example. Find an equation for the hyperbola with foci 2, negative 2, and 2, 8, vertices 2, 0, and 2, 6. Please pause the video and work on that. Here we see that the foci and vertices are along x equals 2. So that tells us our equation is going to be of the form y minus k squared over a squared minus x minus h squared over b squared is equal to 1. And it's always helpful to plot and get an idea of what the graph will look like. So we have foci 2, 8 and 2, -2. We have vertices 2, 6 and 2, 0. And so we recognize that the center of our graph is at 2, 3. And so h is equal to 2 and k is equal to 3. We also need to find a and b, and then we can set up our equation. We know that a is the distance from the center to a vertex. So that's going to be 3 here. So a is equal to 3. And c is the distance from the center to the focus. That's going to be equal to 5. So c is equal to 5. So that tells us b is going to be equal to 4. We have our 3, 4, 5 Pythagorean triple. And so our equation looks like y minus 3 squared over 9 minus x minus 2 squared over 16 is equal to 1. One more thing before we conclude the lesson. Notice that the form of these conic sections, when multiplied out, looks like ax squared plus cy squared plus dx plus ey plus f is equal to 0, where the product AC being positive gives an ellipse, the product AC being negative gives a hyperbola, and product AC being 0 gives a parabola. We're going to build on this in the next lesson when we talk about rotated conics. And this concludes our lesson on conic sections.